In this video, we're going to get in the real heart of the chapter, which is going to be discussing how atoms absorb and release energy in the form of light, and how we go about measuring that energy via a process known as spectroscopy. To start, we'll go over a quick list of the learning objectives in this particular video. First, we'll start with a recap of the Bohr model. We're not going to go over the model itself again, but we'll talk about what its strengths and what its limitations are. In most people's minds, the Bohr model is not what they really think it is. Once we have a firm grasp of what the Bohr model is, the next step in the process is to talk about atomic absorption and release of energy. It's this absorbing and releasing energy that generates the light we have seen in class so far. Finally, we'll wrap this up with a talk about the science that actually goes about measuring this, and that's the science of spectroscopy. What is being measured, how does it relate back to atomic structure, and then finally, we'll wrap up and talk about different types of spectroscopy. Just as a quick primer into the things we'll be getting into later in this chapter, over here on the right, we see a completed spectrum from our actual sun. And you can see here, this is a very, very zoomed in rainbow. We start from the top left corner, and we kind of cruise through all the rainbow colors until we get to the bottom right corner. What you'll notice that's interesting about this rainbow is that there are gaps in it. There's these little holes where the light that we would expect to see is somewhat disappeared. This is a form of spectroscopy, and what's happening is as light leaves our sun, certain wavelengths are being absorbed by certain types of elements. And the location, those absorptions, I guess I should say, are causing these black spots on our graph here. The locations and the size of those blocks, or those spots, is what allows us to identify what elements our sun is actually made of, because certain elements absorb at certain wavelengths of light. Anyway, we'll get more to that towards the end of the video. Let's dive right into the actual discussion of the Bohr model. We'll start by talking about the Bohr model as a visual model of the atom, meaning this is what people expect to see if they zoom down and are able to see an atom firsthand. We'll start with the idea that electrons travel in concentric rings around the nucleus. I have a picture over here on the right showing that. Electrons always occupy the lowest available ring. If we were to put our first electron in our model over here, it would live here in this first ring. As we've talked about in previous videos, this ring holds 2 electrons. We would then move on and start placing electrons in the second ring as we keep going through this process. We also mentioned the fact that each ring has a maximum capacity for a certain number of electrons. And then finally, the arrangement of those electrons based on this model predicts the chemical properties of our atom. And that's really, if you recall, this down here is the purpose of these atomic models, is to be able to predict chemical and physical properties of our atom itself. Well, it turns out using the Bohr model as a visual model for the atom is actually not a great tool to use. It doesn't really represent what electrons are doing. It's a far too simplistic model, and we have since replaced it with better ones, as we've already talked about earlier in the year. First of all, if you want to talk about things that don't make sense, electrons definitely do not travel in concentric rings around the nucleus. Their path is much more complex than that, based on the complex nature of what an electron really is. Secondly, electrons do not always occupy the lowest available ring. They can move from ring to ring based on being expelled or being exposed to outside sources of energy. Each ring does indeed have a maximum capacity, but what we'll learn about later on this chapter is that the rings themselves are not the right way to think about it. There's different things, but they do have max capacities. And finally, our last bullet here, this model is actually capable of making certain predictions about the chemical properties of an atom, but those predictions are necessarily limited because the model itself is a little bit too simple. It's only able to make some predictions about some characteristics, and it's ineffective with others. Later on in this chapter, we're going to replace the Bohr model with a better visual model, and that's going to be the Schrödinger model of the atom. But until then, we can talk about the fact that the Bohr has its limitations, but it also still has its uses. The better way to think about the Bohr model is not as a visual picture of the atom, but as an energy model. Each ring doesn't represent the location of an electron, it represents the possible energy levels of an electron. So possible energy levels is the key here. Meaning, when an electron is on ring 1 versus on ring 2, they're not spatially different. They're not necessarily in different locations, they're energetically different. As you move from one ring to the next, the higher number of the ring, which is our value of n, means you have a higher quantity of energy, not that it's farther away. So let's write that in there just to make sure we have that. Not farther away. And as we've talked about in the previous thing, electrons can absorb and release energy, and that results in electrons changing from one level to the next. So absorbing energy would cause our electrons to go out, and then releasing energy would cause our electrons ultimately to fall back down again. And that's what we're saying here. As we move outwards when the energy is absorbed, and our electrons move inwards when the energy is released. So this is really the way you want to think about the Bohr model, not as a place to show us where electrons are, but as a model that shows us how much energy each electron has. And being further out in the rings corresponds to having larger amounts of energy. Now this brings up a very interesting characteristic that scientists started to notice right around the 1900s, and that's the fact that electrons can only absorb or release the exact amount of energy needed to change one or more levels. And this limited the different types of, or different amounts, I should say, of energy that an electron could actually have. Another way of saying this is that electrons can never have an amount of energy that is between two of the energy levels. Now, if that's a little bit unclear, let's take a look again at our picture of the Bohr model over here on the right. Again, we can place our electron here in the lowest energy level, and we'll talk about what this is called in a little bit. And then if we exposed our atom here to an outside source of energy, let's say, for example, we put it in a flame, which is exposing it to heat or infrared energy, these electrons can absorb that. However, if we only put in a little bit of infrared energy, maybe it's only enough energy to get the electron to go from here to halfway between. Well, as we just pointed out, that's impossible. Electrons can't land halfway in between. If your electron doesn't receive enough energy to jump to the next level, that energy would be ignored. Let's say, for example, then, let's take it a step further and introduce even more energy into our atom. That might be just enough for our electron then to jump from the lower energy level up to the higher energy level. So we actually were able to do a jump there. And let's take it one step further still and put in even more energy. If that more energy was enough to get us up here, again, we can't land in between energy levels. Electrons can only absorb exactly enough. That electron would jump up to the second level, and it would absorb, or would ignore basically this excess energy. We could even go one step further and say maybe that electron absorbed enough energy to jump up to this second level here, or the third level, I should say, and that's a legal jump as well. So really what I'm trying to point out here is that as long as an electron absorbs enough energy to jump to any other level in the atom, that absorption can actually occur. If it's not the right amount of energy, if it doesn't match, either the electron will absorb just as much as it needs to get to the next level, or the electron will ignore the energy altogether. Now, this brings up an interesting branch of science that was born as a result of this concept. We're only going to touch the surface of this, but it's a very deep and basically fundamentally altering science that has changed the way we look at the universe. And that is a science known as quantum mechanics. And quantum mechanics is basically the physics used to describe the mechanics. If you guys remember from last year, mechanics is like a ball rolling off a table. But it's used to describe mechanics at a very small scale, things like atoms and subatomic particles. And what scientists have realized over the years is that their behavior, atoms and subatomic particles, is dramatically different than the behavior of a large-scale thing, like, for example, a ball rolling off a table. Because, as we just talked about, atoms can only gain or lose energy in discrete chunks, they behave differently. We don't notice this different behavior in the big world. We see the world as being very continuous. It's a smooth transition from one thing to another. But as you zoom in and zoom in and zoom in, the end result is that once you get down to the atomic level, those smooth transitions that we expect to see are replaced by steps, individual jumps, as electrons jump from higher levels to lower levels. So this very dramatically changes the mathematics and the behavior of particles in this atomic world. An analogy of thinking about this would be comparing, say, for example, a slide versus a staircase. A slide is what we would describe as a continuous system, meaning there is a smooth path from the top all the way down to the bottom, where this is what I would describe as regular mechanics. The staircase, however, represents the quantum world, meaning I can only go from one level on the staircase to the next level, or one level on the staircase down to the next level below that. I can never land anywhere in between these staircases, and if you ever try to do that on a staircase, you know exactly what I'm talking about. In this world, there's a limited number of possible situations that we can have, possible configurations, and as a result, we have to treat that mathematically different, and we have to treat that from a perspective a little bit differently. Now, quantum mechanics, as I said, is a whole huge branch of science unto itself. That's as far as we need to go into it. But just recognize that quantum mechanics stems from the fact that atoms are forced to absorb or release energy in certain chunks based on the spacing of their energy levels. Now, let's get into the heart of the matter and actually talk about how atoms absorb and release energy and how that translates into an atom giving off light. So, if we have a picture here again of our Bohr model, what we can have here again is we'll place an electron here at this lower level. This is known as the ground state. We can describe that here. So this is our ground state. And in the ground state, electrons are at the lowest available energy level. If you remember from how we put Bohr models together, this is where we naturally place our electrons in the lowest available energy level. Now, here's where things start to digress a little bit from how we've talked about before. As I mentioned before, we can expose our atom to certain quantities of energy. And that energy can come in pretty much any form that you want. It can be heat, it can be other types of light energy, it doesn't really matter. We can expose that energy, and the part of the atom that can absorb that energy is the electron itself. And when the electron absorbs energy, that allows it to get promoted up to a higher energy level. And then we get an electron here at the higher energy level. Let's place it up on the top here. This is what's known as the excited state. In the excited state, basically you have electrons that are promoted to higher energy levels. And again, this occurs because we've introduced an outside energy source that those electrons were able to absorb. Now, we've absorbed energy that caused our electrons to jump up to higher levels, and you can imagine the reverse is also possible as well. This electron then has the opportunity to fall back down from its higher energy level back down to the lower energy levels that it originally came from. And depending on the situation you're in, it could fall down to the second level or fall back down to the first level. Both of those would be possible. In each situation, if we absorbed energy to go up, electrons have to release energy to fall back down, and regardless of the type of energy we absorb, the released energy always comes out in the same format, and that's going to be released in the form of light. Since there are two different types of jumps this electron can make, the end result is we would expect to get two different types of light out. That's because the energy of the light corresponds to the gap in energy between each of the individual energy levels. So for example, we could call this E1, and we could call this guy over here E2, the big jump there. This light then, jumping from the little jump from ring 3 to ring 2, would have the smaller amount of energy, E1, and this light here would have the larger amount of energy, E2. And as we've talked about earlier in this chapter, this energy eventually corresponds to a wavelength of some sort, which we see as color. And if you recall that equation, it's this one right down. The energy of our wave is equal to Planck's constant times the speed of light divided by the wavelength itself. Meaning, if the amount of energy in our jump is determined by the structure of the atom, the color of light that comes out will ultimately correspond back to that energy value. By using a spectrometer to measure this, we are able to then calculate the energy associated. And as a result, we can see all the possible jumps electrons can make, and what that starts to create for us is a roadmap as to what this atom actually looks like, where all those energy levels actually are. And if you recall, that's the purpose of this chapter, is coming up with a detailed picture of what the internal structure of an atom comes from. Again, just to recap, we see the light coming out caused by the electrons jumping between levels. The wavelength of that light must correspond back to a specific quantity of energy, and that energy corresponds to the internal structure or setup of the atom itself. Now let's take a minute and put all this into writing so you guys have some listed bullets here. Electrons always start in the lowest available energy level, and we refer to this as the ground state. Electrons have the ability to absorb exactly enough energy to jump from one level to another. Regardless of how much energy I put in, it's always those exact jumps. When it makes this jump, that's what we refer to as the excited state. And then the electrons eventually fall back down. It's a process known as relaxation. They fall back to that ground state and they release the exact amount of energy that was previously absorbed. But in this case, regardless of what went in, the energy always comes out in the form of light. So if it's heat energy, if it's light energy, if it's electrical energy, it doesn't matter. It's light energy that always comes out the other end. Here's the key part then. The color, or more broadly, the type of light, corresponds to the amount of energy between the energy levels. And we can use this last idea here, this is the big point, as a way of building a structure, building a picture of what's happening inside of the atom. We can start figuring out where those energy levels are based on the colors of light that come out, which corresponds again to energy levels. Now, just to kind of get moving towards the end here, just as a quick reminder, here's a picture of the visible spectrum of light. We're going to relate this back to spectroscopy in a second. Here's our visible spectrum of light. We've already talked about the fact that light corresponds to bigger or smaller jumps inside the atom. Let's talk a little bit about that more with our spectrum here. Over here on the side, we got the purples / blue light. And over here on the right, we have the red light. The red light is relatively low energy. This means it has very long wavelengths. And low energy light corresponds to smaller electron jumps. Because the jump is smaller, it's releasing shorter amounts of energy, and as a result, we would expect to get a line on our spectrometer more in the red region. Conversely, over here, purple refers to relatively high energy light. We would expect much shorter wavelengths, and as a result, we would expect larger electron jumps inside of our atom. So I guess what I'm trying to say here is that we start to see colors show up in our spectrometer, we can correspond the color that we see, either on the blue side or on the red side, back to the size of the gap that must have been made in the atom itself. Now, likewise, keep in mind that the spectrum does not stop in the visible range. We can continue this measurement over in the UV range if we had a spectrometer that measured in the UV, and we can continue these measurements all over in the infrared range if we had a spectrometer that measured in the infrared. We are going to be limited in class to just a visible spectrum, but again, we can see lines showing up outside of these ranges. Now, last piece of the big puzzle here before we talk about types of spectroscopy is the actual translation between what we see happening inside the atom versus what we see happening inside of the spectrometer. And again, we have a picture here of our atom again, our Bohr model. We're going to ignore some of the mathematics that's going on over here. We're not super duper worried about that. But what we are worried about is these electron jumps. Now, again, we can imagine we have an electron in our low level here. It's exposed to some sort of outside form of energy, and that causes this promotion. What these diagrams then represent are the different ways that electron can fall back down to the ground state. Notice each different way involves a different sized jump, and this one actually continues out to higher levels. As a result of the different sized jumps, we end up getting different colors of light being released. The size of the jump again corresponds to a certain quantity of energy, and that energy corresponds to a certain wavelength of light. So we end up seeing different colors. To measure this then, and this is where it gets really interesting, we would use a spectrometer, and that spectrometer would take the light that we would see, separate it by wavelength, and we would see something like this show up on our spectrometer. This red line here corresponds to this electron jump here, this very small one, and it gives a very low energy red light. The aqua or the blue-green one that we get here corresponds to this jump, a significantly higher. And then we've got two more jumps here in the purple range. One of them is clearly visible here. That would be this jump from ring 5 down to ring 1. And then we've got another one that's a little harder to see over there. If you really look closely, you can see it very, very faintly, but in actuality, it's very difficult to see. That would correspond to this particular jump, and the reason it's hard to see is simply because it's outside of our visible range, or it's at least very much close to the edge of our visible range, and as a result, it's harder for us to perceive. The real point of this picture overall, though, is that atomic structure corresponds to the arrangement of lines on our spectrometer. So the arrangement of lines over here corresponds to the different size jumps that electrons can make over here. The bigger the jump, the more blue of a line we get. The smaller the jump, the more red of a line we can get. And again, you can see how we can then be using our spectrometer to start figuring out how are these rings arranged inside of an atom itself. So that's the majority of the heavy lifting for this video. Before we wrap things up, I want to talk about two different types of spectroscopy. The one we're going to be dealing with primarily is known as emission spectroscopy. In emission spectroscopy, you basically crowd the atoms with tons and tons of energy, and typically it's either electrical or heat energy. Electrical from like one of the light boxes, heat in the form of a Bunsen burner flame. As a result, the atoms absorb exactly as much energy as they need. That causes electrons to promote to higher levels, and when they fall back down, we get the brightly colored lines here that we see here. And this would actually be an image of a spectrum for the element hydrogen. We see two darker blue lines over in the end. We see this aquamarine here, and then finally we see the red line way over on the left, similar to the atom we were just taking a look at. So this is emission spectroscopy. You absorb energy, and atoms release light. The second type of spectroscopy we look into is absorption spectroscopy. In absorption spectroscopy, you basically bombard your atoms with a full spectrum of all possible lights, all of the visible light spectrum. Because the atoms can only absorb exactly enough energy to make specific jumps, what we end up seeing, and this is what we looked at earlier in our video, we end up seeing these little gaps that show up here. And these little gaps basically represent the specific energies that your particular atom could absorb. Those energies were absorbed. Now those atoms then re-release that energy, but they re-release that energy in a bunch of scattered different directions. And as a result, we don't see that energy show up on the spectrum. As opposed to the emission spectroscopy, we end up getting a specific arrangement of black gaps per each element, as opposed to with emission, we expect to see the bright lines. What's important to note, though, is that the spectrum should be identical. And here we see the emission spectrum and the absorption spectrum side by side. Notice the locations of all of the lines are identical with one another, and that's because whether you're emitting the light or absorbing the light, electrons are still jumping between the same levels. Since both of these spectrum represent the element hydrogen, we would expect the locations of those lines to be identical, and they most certainly are. It's basically just two different ways of getting at the same bit of information. So let's wrap this up then. At this stage in the game, you should be able to do a couple things. First of all, you should be able to describe the Bohr model in some new light, maybe talk about some of the misconceptions people have about the Bohr model, and more importantly, talk about its real purpose. It's an energy level diagram, not a visual picture of what an atom really looks like. You should also be able to explain how atoms are able to absorb and release energy and how this translates into the light that we see that corresponds to each individual element. Finally, you should be able to explain how spectroscopy is used to measure the internal energy states of the atom. The idea that those energies that come out in the form of light that we see as wavelength correspond back to energy gaps between the rings in the atom itself. And finally, you should be able to describe the differences between absorption spectroscopy and emission spectroscopy. They measure the same exact stuff, we're just going about it in a little bit of a different way. During class time, we're going to go over this concept yet again. I find this is something students have a hard time grasping, and the more times you see it, I think the easier and easier it is to understand what's really going on. Ultimately, however, this will lead us into the science of spectroscopy, how atoms can be, how this can be used as a tool to either discover about atoms or to actually measure the other characteristics of atoms as well that are related with its ability to absorb and release light.